see. Okay. Okay. All right. So, hello everyone. Well, thank you, Margarita, for mentioning our work. Well, unfortunately, I'm not including any of them in the slides. Okay. Another unfortunate is this work has nothing to do with learning. Okay. The only good thing is it does have something to do with the construction. Well, to some extent. Okay. So anyway, today I would like to share some of our work on LiDAR mapping and some of our attempts to apply it in construction. So what LiDAR sensors will have been in the community for decades since the DARPA Grand Challenge. Well, the problem back then was that this kind of devices were very expensive, and that makes the integration and experiments on actual robots very challenging. So our interest in the LiDAR sensors starts from 2019. That's the time when the Netvox released uh, the the LiDAR sensor mid-40. So the very different nature of this sensor is the low cost. So it's very cost effective. So has the potential to be widely adopted in robotics community. Well, besides the cost, this kind of sensor is also very unconventional in many aspects, such as the cone-shaped field of view, the very unconventional spiral points distribution, and also the non-repetitive scanning. Well, since it's so different, I thought that there must be something new we can do with it. Well, although we had no idea what we could do it. But anyway, we started research on it. So we developed our first system, Gnome Netvox. So as the name suggests, this system is was largely based on the Gnome framework developed by G back in 2014. So we just took the feature extraction module and also the scan to map module so that it can better adapt it for the small field of view LiDAR sensors, such as the Levox LiDAR. So, well, the system generally works, but the problem is it's very fragile. Well, this is no surprise because the field of view of this kind of LiDAR sensor was so small, so making the feature points in the current scan, has only a very small portion of them are overlapped with the map. So to increase the robustness of the system, so the next work we developed was a FastLeo. So here we integrated the inertial data. Well, because the inertial sensor, well, it has been integrated with visual sensors and LiDAR sensors in many previous works. Well, in this one, we consider what the Nivox LiDAR again. Well, because the small field of view makes it very challenging. Well, we considered a common filter framework because of its efficiency, but unlike the conventional common filter, where the common gain was computed based on the covariance matrix, we derived a new common gain based on the information matrix. So the new common gain has a multiplicity that depends only on the number of states instead of the number of measurements. Well, because for LiDAR sensors, the features, the number of measurements are often very high, up to thousands, while the number of states is often just tens or less than 20. So this can make the common filter even more efficient. Besides providing a good state prior, the inertial data can also be used for in-scan motion distortion compensation. So this was achieved in a backward propagation. So that makes the fast Neo. So generally, the system works stable and also accurate, but only in small environments, because after each scan, it has to build a k-dimensional tree from all the scans. So to address that problem, so we further developed a incremental KD tree. So to address the time consumption for constructing a k-dimensional tree. So the incremental KD tree now it only rebuilds only part of its branches. So it takes only new points in and rebalance the branch that is found unbalanced. So since the only a certain branch of the tree has to be rebalanced, so the whole k-dimensional tree does not have to undergo a complete reconstruction. So this can reduce the time consumption for mapping. So since the system is so efficient, so it enabled us to register the raw points of a new scan. Okay, so well, this registration of raw points is also known as a direct method in both visual SNAM and LiDAR SNAM. So the overall system was tested um, in different scenarios and on different platforms, such as a mobile platform, moving a campus environment, a handheld devices in a factory plant, and a micro drone performing aggressive flips, and also a larger drone performing a airborne mapping. Well, the last scenario was very different from the previous works because the view is from sky to the bottom to the ground. Okay. Um, the system is also very efficient. It's able to run in both Intel processors and ARM processors. So it also enabled us to develop many of the subsequent works on autonomous navigation of drones. Okay. So after release work, we have received many inquiries from the industry about the availability of these devices and also the software. So this motivated the students to commercialize their systems. So the students Xu Wei and Qin Youming, later on they founded a company known as Manifold, focusing on the development of the portable mapping system, both hardware and software. So their devices have been used in many interesting scenarios, like the smart mining, the automatic BIM generation, the Renix digitalization, and also the interior design and construction, etc. Well, but our research still has to continue. In the subsequent work, well, once we are able to build a point cloud map in real time, we're considering can we do the meshing tasks also in real time. Okay, so meshing is often very time consuming, and we have to build like a distance field. Okay, well, this distance field could take a long time to build, especially on CPUs. So to reduce the computation node, what we do is we project all the 3 points, 3-dimensional points into a local plane, and then we do a 2-dimensional mesh on this 2-dimensional plane. So since the dimension has been reduced from 3 dimension to 2 dimension, so the meshing can also be more efficient. After the meshing in the 2-dimensional space, we can unproject it back to the 3 dimension. So in that way, we obtain the 3-dimensional mesh. So as a consequence, we are able to build the mesh of a quite large environment. We also consider the place recognition problem. We propose the so-called triangle descriptor. Triangle descriptor. What we call it BTC because this triangle is combined with a binary descriptor that is attached to each of the vertex of the triangle. So, well, that's more on the odometry parts. So another attention of our work is also on the boundary adjustment problem for LiDAR points. So the motivation was that in most of the odometry system, we considered a so-called pairwise registration. Well, for pairwise registration, especially when the LiDAR field of view is very small. So the accumulation could often be, the drift could be accumulated very quickly. So to reduce this drift, in visual SNAME, researchers have been done a windowed boundary adjustment. Okay, so in the boundary adjustment, the camera poses and also the feature parameters are being optimized simultaneously. So we were thinking, can we do the similar thing for a LiDAR sensor? Can we do a similar boundary adjustment also for LiDAR sensor? Well, for LiDAR sensor, a natural feature could be the line feature or the plane feature. Okay, so once we choose the feature, so a natural residual would be the distance between the point in a new scan and the feature, the plane or the edge, or the line. Okay, so this one leads to a point to plane distance and also point to edge distance. Well, in the prior case, the point to plane distance is also identical to the residual used in the plane adjustment proposed by Zhou and KS sometime a year earlier. So what we did was, we did a little bit more neat algebra derivation. We found that the features can actually be solved analytically in closed form. So either for the plane feature or for the edge feature, they can be solved beforehand before we actually optimizing it. So the solution is known as is associated to the eigenvectors of the covariance matrix, and then we can substitute the solved plane feature back to the cost function to the residual, and then the residual eventually become in the form of eigenvalues of the covariance matrix, and moreover, the residual is now only a function of the pose. Okay, so this has a very important implementation because it essentially eliminates all the feature parameters from the boundary adjustment. Okay, so since in many boundary adjustment problem, the number of features are often way more than the number of LiDAR pose. So elimination of so high number of feature points, so feature parameters could reduce the optimization dimension dramatically, and this will have a potentially more efficient boundary adjustment. Okay, so with the formulation of the cost function, we also have to consider how can we solve it. So although the cost function is in the form of eigenvalues, but it really represents a square distance between the point and the plane or edge. Okay, so for a square distance is quadratic. So for quadratic cost function, a natural solver would be a second order solver. So yeah, so we consider second order solver, but to do so, we found that this can indeed be done because we can derive its Jacobian and also the Hessian also in a closed form. Okay, so the derivation of the Jacobian and the Hessian makes it possible to formulate the boundary adjustment problem and also to solve it efficiently with a second order solver. So we also have to consider the feature association problem. So we use the adaptive voxelization. We divide the space into voxels of different sizes. So points from different scans in the same voxel are considered as associated features. So we integrated this technique into a norm framework, and we verify if it's able to mitigate the drift problem in the odometry. Well, the results show that indeed it's able to reduce the drift to some extent. Well, this is no surprise because it takes more time. It takes additional time, right? Because we have to perform an additional windowed boundary adjustment. Well, although the additional time is well within the real-time operation constraints. Well, as a general technique for multi-view registration, the boundary adjustment should be able to work for general LiDAR mapping tasks. But we did this. We applied it to a large scale, global mapping of LiDAR scans. But we found that it's still very time consuming. The problem was that the evaluation of the cost function, the Jacobian and the Hessian, they still have to enumerate each individual point. Well, for LiDAR sensors, the LiDAR points are often, very large in number. So enumeration of this large number of LiDAR points could take a dramatic time. So to address this problem, so we leverage the technique, the point aggregation technique. That has been used in the plan adjustment and also the eigenfactor. So essentially, all points associated to the same scan, lying on the same feature, they can be represented compactly by a 4x4 matrix. That's a so-called point cluster coordinates. Okay, so with the point cluster, we don't have to enumerate each individual point. Okay, so that can save dramatic time. So we showed that the residual can indeed be represented by this kind of point cluster. And also, to enable a second order solver, the Jacobian and the Hessian can also be expressed in terms of the point cluster. Okay, so that would enable us to evaluate the costs and to solve it with a second order solver without the enumeration of each individual point. So a side task we did was also we derived the uncertainty in terms of the covariance matrix that is also represented by the point cluster. So we tested this technique. We term it as BOM2. It's a successor of the previous boundary adjustment technique, BOM. Okay, we tested it in simulation in terms of efficiency, accuracy, and consistency. It's able to converge often in a few steps and achieve fairly accurate results. We also tested it in real-world data, the previous year HLT SNAM challenge data. So in most of the sequences, the accuracy, the global accuracy is a few centimeters. And besides the post accuracy, we also examined the map accuracy. So the map accuracy after the global mapping can also be reduced within 2 centimeters. So this map accuracy is already at the level of the measurement noise of a LiDAR sensor. So that means the LiDAR movement, the motion has been fully compensated. So we can achieve a map accuracy that just like the LiDAR sensor is placed static there. So we could also put back the image measurements in the boundary adjustment problem. So the point cloud data with the boundary adjustment can provide very good prior information, such as the occlusion between the scene and the scan, and also the local geometry of visual features. So this can facilitate the image alignment process. So eventually, we are able to achieve a cornerized point cloud almost photorealistic. So finally, I would like to share some of our recent projects, how we apply all the mapping algorithms into a real world application. It's called a modular integrated construction transportation, MIC transportation. So MIC stands for modular integrated construction. So it's a very new construction paradigm where the construction parts or modulars, they are manufactured in factory, and then they are transported to the construction site for assembly. So a key problem in this process is transportation, because modular construction modulars are often very large in size and also very heavy in weight. So transporting them would require a very wide turns for the vehicles. So these wide turns may not are vulnerable, especially in urban roads. So even it's vulnerable, so this could cause a significant traffic congestions, especially in rush hour. So the Hong Kong Transportation Department has sponsored a project to address this issue. So this project aims to perform three tasks. One is to perform the swift analysis for a given route. The second is to perform a swift path-aware routing. And the third is to conduct a traffic impact analysis. So nine is the bottom of all these three tasks is how to obtain a detailed and accurate three-dimensional model of the urban roads. So that's where the part, we can contribute to the project. So we develop a portable sensor suit consisting of a LiDAR sensor and a camera. So we also integrate all the mapping softwares that fuses the LiDAR data, the inertial data, and the camera data. And we develop a software system. So the sensor suit is installed on the trainer of the vehicle and conducted a trial test in Hong Kong Island. So the use of the sensor suits is mainly for two purposes. One is that it's able to estimate the trajectory of the trainer and the track of the vehicle. Based on the trajectory, an accurate and realistic kinematic model of the vehicle can be estimated. So based on the estimated model, so the platform can perform the coordination verification and also the feasibility assessment for a given route. So the other purpose using this sensor suite can enable us to obtain a detailed and accurate three-dimensional model for for the traveled urban roads. Well, this is not very new because there are existing systems that can do the road mapping very well. But those equipments are often very again high cost, and this high cost will limit the possible wrongs we can use it. So like the Hong Kong government already has a vehicle that can perform this kind of three-dimensional mapping, but that's a whole vehicle. It costs a few millions Hong Kong dollars, and they can only perform the mapping in just a few times, like a month. Okay, so once the device cost gets lower, we imagine that this kind of technique and including both hardware and software can be applied more widely and at a higher frequency, and you can update the road mapping like once a week or once a month. It can be used for mapping for more areas. Okay, not just in the main roads, but also larger areas have a higher coverage. Okay, so well, that's pretty much all the talk. So well, the boundary adjustment, I want to mention a little bit more about the boundary adjustment. Well, the boundary adjustment now has been in the complexity of, that depends on the number of poles. But the problem is solving this Hessian matrix. This Hessian matrix is in the dimension of number of poles, but solving it is still very time consuming because the number of poles, for example, for a city level environment could be thousands, tens of thousands, hundreds of thousands. So solving this Hessian matrix is still very time consuming. So our recent work has showed that this Hessian matrix can actually be diagonalized. So with the diagonal Hessian matrix, the number of iterations could be higher, but at each iteration, the time for solving this Hessian matrix would be much, much lower. So in total, so the solving time would still be much more efficient than existing one. And this is especially true when the number of poses gets higher, like thousands of number of poses. So the global mapping can be can be performed just in a few seconds. Right, so that's all about this presentation. So yeah. Thank you.
Thank you. So we have time for questions.
All right. Yeah, sorry for taking all the questions. I do have a question about FastLeo2 and in general your SLAM methods. The methods themselves are very accurate after initialization. However, when we have very low attitude change initially, they struggle to initialize. Have you ever thought of improving or relaxing the constraints for initialization of that algorithm?
Yeah, thank you for this question. Well, indeed, we encounter many inquiries, and also we ourselves encounter the initialization problem. So later on, we actually developed a subsequent work. It's called ALI init. So that work we consider systematically the initialization problem. Well, unfortunately, that was released after the FastLeo. So most of the people probably don't know it. Yeah.
Okay, thank you very much.
Yeah, sure.
Question.
Thank you for the great talk. I think the BOM result is great, but I think there's a recently LiDAR-based neural representation-based mapping. So many researchers there. So I'm curious about your research group is interested in such kind of research topic and doing some research or results.
Can you repeat it again? Which kind of topic?
Neural representation.
Neural representation?
For nerve.
Oh, okay.
Yeah.
Neural representation.
LiDAR, especially LiDAR-based nerve.
Well, the short answer is for sure yes. Yeah, so we are definitely interested in the neural representation. So this is very interesting because, but we are more interested in like a hybrid. How can we combine the LiDAR measurements with the visual measurements to make the nerve more efficient, and also that can help the LiDAR SLAM, in terms of its accuracy and also completeness. So LiDAR SLAM has a problem is that the mapping accuracy is fundamentally limited by the point measurement noise. Sorry. So for LiDAR sensors, the typical point noise is a few centimeters, and we cannot do better than that. But this could probably be solved by, for example, because for example, for a structure, we don't measure just one point, we measure many points. And with many points, we can do, well, intuitively speaking, we can do average, right? And average could be like, we can fit like a distance field on it. And this could where we thought the neural representation could come in and to boost the accuracy of LiDAR mapping. And another thing is LiDAR points are often very sparse. And especially for mobile mapping, you just go without caring about which part has been scanned and which part is not. But it's very often that there is some spaces there is no points at all. And so if we render a point cloud map, so you can easily find there is many black holes. Okay, so but the image has actually seen it, has observed it. So we are considering why don't we leverage the visual measurements to compensate the part that is not scanned by LiDAR sensors. Okay, so in return, the geometry provided by LiDAR points could also, for example, facilitate the ambiguity in nerve. It can provide a very good geometry prior, and also it can accelerate potentially the speed of the training, things like that. But we are still on the way. Yeah, this is just something that came into my mind now. Yeah, sure.
Thank you.
Mhm.